All right. Now that we've done some vector analysis techniques using forces and fields for electrostatics problems, we'll show that defining some scalar quantities can make our life a lot easier sometimes. So we'll start by defining a potential energy, UE, electric potential energy, between two charges. So again, it is a system quantity. A single charge can't have potential energy, but a system of charges can. We're defining it as the net input of work from an external force to assemble a charge distribution. So why we like energy is because it is a scalar, so no directions or components attached to that. By definition, we're going to set the potential energy to be 0 when two charges are very far apart, because it doesn't cost any energy to keep those charges infinitely far. And the sign of potential energy actually could be positive or negative. And we can make an analog here to the attractive gravitational force that we looked at with planets. So if two charges have the same sign, they repel. So the external force must add energy into the system to prevent the charges from accelerating away. So that's why we call that positive potential energy. But if charges have opposite signs, that is negative electric potential energy, which students often have an issue with thinking about why this energy is negative. And one, it has to do with the fact that only changes in potential energy are meaningful. So it's totally okay that the potential energy is negative. But to get some intuition behind it, if you try to bring together unlike charges, they're going to accelerate towards each other. So if you're a force bringing these charges together, you have to be doing work to sort of steal that kinetic energy they would have. Another way you can think about it is similar to this idea of a binding energy or an escaping energy needed for a rocket ship on a planet, where you're sort of an energy debt. So these charges down here, this positive and negative pair, this is an energy debt. So the only way that these charges could sort of escape their debt would be a net input of energy to break apart this combination. And we can see the heights of the bars are just related to how close they are, because it would cost me a lot more energy to bring two positives really close versus two negatives just a little bit separated. So let's kind of gain some intuition with this using a ranking. So we have a bunch of identical insulating spheres. Everything's identical about them, except some have positive charge and some have negative charge. So we are going to be interested in ranking the work required by an external force, and that is just a very long way of saying we are ranking this potential energy, because work required by an external force, that's just the definition of potential energy. So we can rank all of these. And I'm a big bar chart fan, as many are in AP Physics, so we are just going to visualize each of these energies using a bar chart. So I'll just set up each of my bar charts here for my 6 charge distributions. And of course, the only thing we can really compare is distances and signs. So there's not a whole lot of like quantitative analysis we could do here, but let's just start. All right, case A. These are two positive charges. We said two positive charges have positive potential energy, and since they're close together in comparison to some of the other cases, we would say this is a large amount of potential energy. So we could say this is large and positive. While in case B, it's still positive potential energy, they're just farther apart, so it wouldn't cost me as much to do that. So for example, I might draw myself maybe like 2 bars of positive potential energy. But in case B, I might draw myself only 1 bar. So this would be a small positive. And we can see how the analysis will proceed for the rest of the cases, because in case C, it is even though it's negative charges, this still would be a repulsive force that we're fighting, so it's still positive potential energy because both charges are negative. So C and D are going to entirely mirror A and B, because it's the same distance relationship. And then E and F, well, E, the charges are opposite signs, so it's going to be negative potential energy. But they're far apart right now, so this would be small negative, so maybe 1 bar of negative potential energy, and then for F, this would be a large amount of negative. So now we can just do our ranking. So we do actually want the sign involved here, most negative to most positive. So if I'm looking for negatives, I only have 2 that are negative. F is a large negative. E is a small negative. And then for small positive, I have a tie between B and D. And then for large positive, I have a tie between A and C. So again, we could really just use our words that we just talked through, our bar charts, our justification enough. So this was, maybe I'll do a little indicator that this was really negative, this was slightly negative, these two were slightly positive, and these two were very positive. So, of course, my formal solution for this involves a lot more text. Electric potential energy is positive for charges of the same sign, negative for charges of opposite sign. So that at least gets us the sign aspect, and then to compare the magnitude, you just look at the separation. So as such, these bar charts allow us to accurately compare it. And for our next problem, we're actually going to use the same charges and look at an interesting trend here. So we will copy this over, because it's the same charges here. And we're going to be interested in looking at what happens to pairs of charges after they're released, and how releasing charges affects their potential energy. So we'll get that nice and lined up here. And this allows us to just quickly determine what's going to happen. So if we look at the first example, case A is not happy, because these are two positive charges that are close together. And of course, I say they're not happy. Here's our obligatory announcement that charges don't have thoughts and feelings. I could say A is not in a favorable state because there's a repulsive force, but what's the fun in that? So case A is unhappy. Case A is unhappy because two positives are close together, but if I press play on case A, it will turn into case B. And we see what happens as I go from 2 plus bars to 1 plus bar, which is a decrease in energy. Potential energy, at least. Then, case C, same idea. Two negative charges, they're going to repel. And that will become case D. I lose a bar of potential energy. In case E, they're unhappy, but for a different reason. These are two charges that are attracting one another. So if I press play on E, the charges are going to come together and create case F. And in this case, my bars are getting bigger. There is a larger amount of bars, but it's negative. I'm going from -1 to -2, and that is a decrease. Because if your bank balance is -$100, and then your bank balance the next day is -$200, it's still a decrease in balance. So we can see our general trend here is that if you press play on a charge distribution, it is going to seek a lower potential energy state for the system entirely. And this will never happen in a vacuum. This is never just the entire energy bar chart for the system, because there's also kinetic. So anytime you're losing bars of potential, that is being gained back in kinetic. So there's some not drawn kinetic energy bars for this. And of course, we'll analyze that when problem solving later today. Now let's talk about some signs. So by definition, work can be thought of as the net change in energy of a system. And in our cases, we're always going to be changing these systems while the charges are at rest. So any change in energy is going to manifest itself in the potential form between the charges. And we could also look at the work done internally by the electric force, which will always be opposite of the work done by the external forces. And you can think of that using an energy conservation approach, using the fact that any work done by the electric field might manifest itself in terms of kinetic energy. You could just take this as a definition as well. Or you could resort to the mechanics version of this, where you just consider work is positive if the charges go the way the force wants it to. But I like to just take these as definitions. It's less gymnastics, in my opinion. We can visualize this with a bar chart. So we are going to draw a bar chart, and we are just going to indicate the sign of the different works. So first, we have separating two positive charges. So if I have two positive charges that are close together, I will call that a large positive amount of potential energy. But if they're separated, it's still a positive potential energy. I just have less of it. So we can see that in this system, because these are external forces doing these things, energy is not constant in the system. And that's totally fine, because something outside is changing my energy. So I can see in this case, well, if I went from 2 bars to 1 bar, something had to come in and take a bar of energy. So the external work done is negative. And either by applying the definition, well, let's just start by applying the definition. If we call this a definition the work done by the electric field is positive. Now, if we looked at this with the mechanics approach that says just look at the sign of the work by looking at how the charges are moving, well, these are positive charges, and the positive charges are repelling each other, and I'm moving them apart. So that is the way the electric force wants them to go, so it's positive. Bringing opposite charges closer together. Well, if I have two separated charges, this is going to be a small amount of potential energy, and since they're opposite charges, these charges are in debt, because I'd have to pay energy to separate them, versus pay energy to get them together. And if I move them closer together, well, they're still in debt, but they're just going to be even more in debt than they were before, because now they're closer together, so it would cost even more to separate them. So my balance went from -1 to -2, so that is a negative change. And the work done by the electric field is always opposite. And again, we can see this works with the mechanics definition because these two charges do want to get closer together, so I'm doing what the field wants. So my electric field is doing positive work. Separating opposite charges to infinity. So, well, we already said earlier that if I had two opposite charges that were separated by some reasonable distance, this is just going to be a small amount of negative potential energy. But if they're infinitely far apart, well, there's no debt at all, because that's what it means to be free from the bounds of each other. So by definition, we set UE equal to 0 when charges are very far apart. So in this case, my balance was -1, and then I'm at 0, and that is an increase in energy, so I have done positive work on the system externally to get this happen. Because originally my charges were in debt, and now they're not in debt, so I had to pay money into that. And by definition, the electric field is doing negative work in this process. Because do the charges want to separate? Absolutely not. That's against what the electric field wants. So of course, now let's calculate it. Now that we know what it does qualitatively, we'll pull out the quantitative. This looks familiar. It looks almost like Coulomb's law. So we said Coulomb's law, because it's related to forces, has two charges. So we should compare this to Coulomb's law, which says the electric force is KQQ over R squared R hat. So there's two main changes for this. One, it is a scalar, so there's no vectors involved, which many of us will find to be a nice change. And second, it just involves an R instead of an R squared. So one thing to note with this is electric potential energy is a scalar, so use signs. So I typically don't use signs with vector quantities because we get the direction correct, because arrows don't have a sign. Vectors just have an orientation, but these are scalars. You can have a positive or negative bank balance, so we should be using signs of the charges here. And as per usual, you can use superposition. So if you've got lots of charges, just add up all the pairs of energies to get the total energy of the system. So let's think about why this is consistent with our rules from the previous part. First, we want to look at the positive-negative rule. So we said that if the signs are the same, you get positive potential energy. And that is going to be related to the numerator, because we have two things multiplied together. And using our middle school math rules, we know that plus and plus make a plus, and minus make a plus. So this is just related to that rule. It's because we're dependent on Q1 times Q2. So since it's the product of the charges, you get a positive number when the signs match. And then our second rule said that the more separated you get, the lower the bar height is going to be relative to 0. And that's just based on the inverse nature, right? We see we got to divide by R. So if you have a big separation, you're not going to have very much potential energy and magnitude. Your charges will either cost very little to get there if they're both of the same sign, or it wouldn't cost very much to free them from their debt if they're far apart. Now let's do a couple quantitative examples. So we have three charges in a line, and I could order them plus plus minus or plus minus plus. So I do think this is a pretty difficult QQT for this first part, where we're going to be interested in comparing which one of these configurations has a greater potential energy of the entire system. So these are the same charges, and we're given in the problem that these distances between each charge is d. I have just changed the order of the charges. So this is a case where you might find it better just to do the derivation of the energy of each system to figure out which one has less and try to figure out how you could have seen that in hindsight. But I'll show you a way to do this because I did write this, of course, so I have to have an answer. So first of all, we can see that I have in configuration A, I'll call out my first pair of charges will be this one. Maybe we can draw that a bit better. Now, this is my closer of the two possible separations because these charges are right next to each other, and it's going to be positive because these charges have the same sign. So I might say this is a big positive contribution. Then if I swing over to my next pair of charges, these charges has an opposite sign, it's the same separation as before, so I'd call that a large negative contribution. Notice these actually cancel. And then my third pair, so again, we have to do all possible pairs. So I paired 1 and 2 and 2 and 3, so I haven't paired 1 and 3 yet. And these are opposite signs as well, but the distance is bigger, so this is going to be a small negative contribution. So I should get a net negative amount of potential energy in configuration A. Then for configuration B, we can do the same technique. I just moved the negative to the center. So we have plus and minus, so it's a negative potential energy, but this is going to be large because the separation is small. And then this is also going to be a large negative contribution because it's opposite signs. And then by separating my two positive charges and placing them on the end, my positive contribution is small. So we can see by inspection here that we have a small negative sort of net result in A compared to a larger negative result in B. So I would say that A has higher potential energy. We don't have to actually tell you we set U to be 0 at infinity. That's more used in the derivation in B, but you can also just assume that's true, unless if we have some weird infinite charge distributions. So this is a justify without manipulating. So we can just use this fact that in B, the unlike charges are closer together, and the like charges are farther apart. So this means my negative contributions get bigger in B, and my positive contributions get smaller. So we get larger negative contributions and smaller positives. So absolutely, without doing any math, we can just reason that B has to have lower potential energy. Another way of thinking about it, which is definitely more hand-wavy, is that particles like, of course they don't have wants and desires, but our anthropomorphized particles would like to be in a low energy state. And this is actually a much more favorable state, B versus A, because that negative sort of serves as a buffer to separate the two positive charges. Again, that's definitely not as conceptually sound, but it's a way maybe to figure out what the checkbox was. All right, now for a much easier task. It's plug and chug garbage time. We want to find each energy type, each energy magnitude, or not the magnitude actually, we just want the actual number, in terms of Q and D. So maybe we can just redraw. So we know what we're going to do is that U is just the sum of all of the KQQ over R's. We just have to match all the pairs. So for A, we get this system where it was plus, plus, minus. So in this case, we get pairing these two charges. Everything is, well, we'll put the Q's here just as a reminder. Q, Q, Q. Just as a reminder, we see that potential energy is K times Q divided by D. So again, remember that you actually do put the sign into this because it's a scalar. Then for the next pair, it's the same thing because we get a K, a Q, and a minus Q over D this time. And then for my final pairing, because again, I can't forget to pair every charge, we get this pairing, which would be a K times a plus Q and a minus Q, except this time the separation is D plus D, which is 2D. Do not square. This is not Coulomb's law. So in this case, UA would just be equal to, the coefficient is going to be 1, KQ squared over D, for the blue contribution, negative 1 KQ squared over D for the green contribution, and negative 1/2 kq squared over d for the purple. So we get 1 minus 1/2, which tells us that UA is just going to be negative 1/2 kq squared over d. All right. So now we'll just do the same technique for B. So for case B, very similar, except it was plus, minus, I don't like that, plus Q, minus Q, plus Q. All right, so blue contribution, we get a K, a Q, a minus Q, separated by 1 tick, D. Then for our green contribution, I need to go all the way up there. Our green contribution would be K times minus Q times Q divided by D again. And then for our purple contribution, we have to do the ends. So that would be a K, a Q, and 2 Ds of separation. So this means that UB would be equal to negative 1 kq squared over d plus another negative 1 kq squared over d plus 1/2 kq squared over d. So we can see that we are going to get a consistent result. So 1 minus 1 is negative 2, and then I add 1/2 to negative 2, so I get negative 3/2 kq squared over d for the potential energy of the system in B. So now we're just asking, is this consistent? Well, we see that UA was equal to negative 1/2 kq squared over d, and UB was equal to negative 3/2 kq squared over d. And we can see that negative 1/2 is bigger than negative 3/2 because B is more negative just as expected. So we see that negative 1/2 kq squared over d is definitely larger than negative 3/2 kq squared over d. So you can see that UA is larger than UB as expected. Oh, and I should be nice here, and I should say consistent. Please actually say it. I should have to explicitly identify it's consistent. All right, now for some less thinking is involved here. We're just going to be doing some pairings. Derive an expression for the total electric potential energy of each system. All right, same idea here. Doesn't matter that it's 2D. This is a scalar. We don't care about direction at all. So this is just done to spread it out. All right, blue contribution. I have a K. I have a Q. I have a minus Q. And I have a side length S. Green contribution. I have a minus Q and a Q. Separated by S. And then my purple contribution, I have a Q and a Q separated by S. So we can see that we're going to get negative 1 kq squared over S, negative 1 kq squared over S, and positive 1, so this works out to negative kq squared over S, which makes sense because there's 2 pluses and a minus, and they're all separated by the same distance, so it makes sense that this is a net attractive system. All right, the square. Here, everything is the same, so we can definitely exploit some symmetry. So first, this is never an issue, identifying that there's these 4 pairings we could make. So I have 4 pairs of QQ that are just a vertex away. But we have to pair every possible set of charges, so we can't forget that this charge has to interact on the diag, and this charge has to interact along the other diag. So we also get 2 copies of that. And we have to be careful about the distance. So again, remember this is a square. So using the Pythagorean theorem or just some facts from geometry, the diagonal, which you could get with Pythagorean theorem, is just going to be s root 2. Because if this is s and this is s, this is a 45, 45, 90 triangle, so this would be s square root 2. Or just Pythagoras it. So this gets us s times square root 2. We could simplify this a variety of ways. So you could get 4 plus 2 divided by root 2 as a coefficient, kq squared over s. Or, if you notice that you could rationalize, if you decide to do that for whatever reason, and you'd get 4 plus square root 2 kq squared over s. I'm usually not a rationalizing person, but this is a case where I'd actually do it because I think it simplifies sort of nicely here. It removes the fraction entirely. All right, so of course, we talk about energy because it is conserved. So this is our same old mechanics situation where if you look at your energy accounting, potential and kinetic can trade if there's no external forces. So if you know the change in potential, you know kinetic has to change opposite that. So we got two identical point particles, and they're given mass, and we know their charge. They're originally fixed in place as shown below. And then we release one of the charges while pinning the other one at rest. So only one of the charges gets to fly away. And we'll see why that happens shortly. All right. So first thing we want to do is calculate the initial and final electric potential energy of the system. Because we know everything we need to calculate the potential energy at each time. So for our initial potential energy, it's just going to be kq squared over r with their initial separation. So for their initial separation, we see that it's going to be 0.1 meters. So I'm going to put in my 9 times 10 to the 9th for Coulomb constant, 40 microcoulombs, so don't forget your 10 to the minus 6. Both of those had that charge. And my initial radius was 0.1. Or sorry, not radius, I should say, separation was 0.1 meters. And if we plug all this in, magically a nice number pops out. This is going to be 144 joules. We can also calculate the final potential energy of the system. So we can do the same thing. I'll actually write it out, but you can see all we did is double the distance. So based on linearity, if you just double the distance, you double the denominator, so you're going to half the energy. I'll write it out just because I think it looks nicer. I say write it out when I just use the copy paste. Look at this. Look at this time saving we got. So my final energy can be found just by doing the same thing, but I just doubled the denominator. So this is 72 joules. So now we can draw a quantitatively accurate bar chart for this system at the initial state and final state. So I should have noted that we're doing it both times. So this would be when they're just separated by a small amount, and this is after we have released the charges. Or sorry, we've released the second charge. All right, so in the initial state of the system, the charges are at rest. So I am just going to give all 144 joules of potential energy. That is just my entire system energy. Because the charges aren't moving. So the entire energy of the system is in kinetic, or sorry, is in potential at this point. Now we can come down here, and so it might be helpful to give yourself like a little E total line maybe, or just a note that in this system, the total energy is equal to 144 joules. So we know this also has to be true, that the total energy is 144 joules. So in this final state, we see the same thing, except this time our potential energy has decreased to 72 joules. So just by accounting, we can see this was actually an exact 50-50 split, where now our kinetic energy is going to make up that remaining 72 joules. And we see this works out, because I have 144 plus 0, that's 144. Or I have 72 and 72. which is also 144. So now we can calculate the speed of the moving charge. So what's important here is that we actually know the kinetic energy of the charge, because we're only letting this charge move. So we know that the kinetic energy at that time has entirely gone to the moving charge. So we'll just use our good old-fashioned K equals 1/2 mv squared for energy. So we'd get 2K is equal to mv squared. So V would be the square root of 2K divided by m. And we can plug in, because we know that the kinetic energy was 72 joules, and the mass of the charge, I gotta scroll, 0.25. Oh, how convenient. That's a perfect square. Thank you, me from the past, for doing that. So we'd get 144, which is 12. Sorry, yeah, 144. This will be, I believe, 24 meters per second. We can check that, which I will do real quick here. Yes. And this is exact, by the way. This does work out nicely. So this is our final velocity of the charge. And it's really important that only one of the charges was moving here, because they're not sharing the kinetic energy, which is exactly what's going to happen in part D. So in part D, it is the same problem, except now we have let both charges move. So they're going to share the potential energy. So what might happen here, if you want to visualize it with a bar chart, is it is the same bar chart where we're going to have 72 joules of potential, except now my kinetic energy actually gets split into two pieces. Because both charges, since they're equal in mass, are going to have the same velocity, so they're going to have the same kinetic energy. So I just have to exactly split the kinetic between the two of them. So in this case, I could do the same analysis as before, where all of this still applies, where we said that kinetic energy was 1/2 mv squared. So V, and we call this V2 this time. So V2 is going to be the square root of 2K over m, but I just might note that this is going to be a different kinetic energy now. So if we do this, we get an answer of, I won't say equal because I do have to do some rounding here. You can't get these both to work. This is roughly 17 meters per second. Notice this is less. This is less than 24. Oh, and I should write that. I should write that somewhere where we could actually read it. So this is less than 24 meters per second, as expected, because this time you're sharing the kinetic energy. But something that's interesting is our velocity originally was 24 meters per second, and now it's 17. And that's not just half. So actually, sharing the kinetic energy didn't half the velocity, which we'll use a ratio approach to just show why that's true. Now, so we said we actually could have used this using our 24 meters per second answer originally, because we said that the final velocity of the particle was just going to be twice its kinetic energy divided by m. And m stayed the same, but k changed. So your new v would be square root 2k over m. So I'm a big multiplier guy. So your k got halved because you're sharing the kinetic energy between the two charges now. So I'm halving the quantity under the square root. So this means that square root of 1/2 times my original v is going to be the answer. So this actually means it's square root 2 on the denominator, which is about 1.4. So this is why we get our 17 meters per second. Because 24 divided by 1.42 or whatever it is roughly 17. So this is why it works out. You actually could have used a ratio approach. I'm sure some of you did. All right, that's enough numbers for me. It's simple math time. All right, so point particle of mass m and charge q is initially a distance r0 from this sphere, and it's launched away. So notice that this sphere is going to be attracting the charge. So this charge is trying to escape, but it's actually not going to. So we say eventually it's going to reach some distance RF and stop, and then turn around and come back. But we're just interested in the moment of stopping. Ignore gravity. So we're going to draw ourselves a bar chart for this scenario. So initially, my charge is as close as it can be in the problem to the sphere. So originally, this is an attractive scenario because it's positive and negative. So I'm going to have a large amount of negative potential energy, and my sphere is launched, so it does have kinetic. And I actually know expressions for each of these things, because our charges are plus q and negative big Q, and our velocity and separation are defined. So this would be negative kqqq over r0. And since my initial velocity was defined, this is 1/2 mv0 squared. Now we can do a similar thing at our final state. So our final state, it has gotten much farther away. So maybe I might draw this state. It's gotten much farther away, but it's stopped. So it stops at this time, and it's a distance RF away. So we actually know our kinetic energy is going to be 0 at this time, because I'm stopped. And then to make energy conservation work, we know that if my energy net for the system originally was 1 negative bar, I'm going to give myself 1 negative bar of potential energy to end with. And this is going to be negative kqqq over rf. Now what we would like to do is derive an expression for v0 in terms of the given quantities. So we actually want to know, given that it stops a distance rf, what speed did I launch it with if it can only reach rf before getting pulled back? So you can use either form of energy conservation for this. You can use deltas, but if you have a bar chart, it's usually easier to use a sum of energies stays constant approach. So I'm going to use that. So I call this the bar chart conservation equation, because you're just setting your bar chart values equal when you sum them. So we said our initial potential energy was negative kqqq over r0. Our initial kinetic was 1/2 mv0 squared. Our final potential was negative kqqq over rf. And our final kinetic energy was 0. What do we want to solve for? We want to solve for v0. So let's get the 1/2 mv0 squared by itself. So this would turn into plus when I add the r0 terms. So I'd get positive kqqq over r0 minus kqqq over rf. We can do some factoring. So we could write 1/2 mv0 squared equals kqqq times 1 over r0 minus 1 over rf. Then we can multiply by 2 and divide by m. So we'd get v0 squared equals multiply by 2, divide by m. So we can get v0 by just square rooting both sides. Quite the number of letters we get in this one here. That's about as much as I'd like to simplify this. This actually is very similar to this question of escape velocity for a planet, because if you launch a rocket, unless you go fast enough, it's going to come back to the planet. So we actually want to talk about what is this minimum VO needed to escape? Well, for something to escape, we're asking how fast do I have to launch the sphere to get it to totally escape? Well, I'm going to use the fact that by escape, we mean that you can get really, really, really far away from the sphere. So if you get really far away from the sphere, that means that RF is going to be infinity, because you have no stopping point. You've made it all the way. Now, if you exceed this V0, you're going to reach infinity with some speed, but at the minimum point, all of your kinetic energy exactly got you far away. So we're just going to plug in infinity, which is of course legal because this is physics and not math. So we can say that the minimum escape velocity is equal to square root 2kqqq over m times the quantity 1 over R0 minus 1 over Rf, which we're saying is infinity now. And again, remember our physics fact that 1 over infinity is equal to 0, right? If I have one cookie to divide amongst infinite people, each person gets 0 cookie. So square root of 2kqq over m times 1 over R0 minus 0 under the square root. So this means our minimum escape velocity is just going to be the square root of 2kqq over m times R0. So that would be our answer. There is an alternate approach you could do to solve this if you didn't want to use the expression from earlier. Instead, you could set the final potential energy equal to 0, because that's what it means by escaping. So you could set up this equation, negative kqq over R0 plus 1/2 mv0 squared equals 0 plus 0. Because you'd have no potential and no kinetic at the endpoint. Again, this is very similar to this gravitational escape velocity equation that you might remember from mechanics with the orbital mechanics. Because again, you can see in this case, v0 squared, after adding the term to the other side, you multiply everybody by 2, divide by m, and take a square root. So we do get that result. All right, lastly, here it is again. The charge along the bisector problem. All right, we got 2 positive charges and then a third positive test charge, and I give it some mass. So it's a place just a distance x along this axis, and we're going to be interested in finding its energy / motion. All right, first, which way is it going to get pushed? Well, just use some force analysis here. Oh, no, I don't want an arrow, actually. I want this one. So again, these would be the lines connecting my charge to my test charge here. So first, we get a charge down and to the right. It would be the force exerted by one. Then we'd get up and to the right from the other. So we can see due to symmetry, we would get a net force that's going to be along the x-axis. So of course, in a lot more words, here's an explanation. Top charge, down right. Bottom charge, up right. Vertical components cancel. Net force is to the right. Derive an expression for the total electric potential energy due to the test charge due to the other 2 charges. So notice this actually doesn't say net charge of the 3-charge system. This says associated with the test charge. So we're only looking at the pairings due to the test charge. And we'll see why based on what happens in part C. So, well, there's only 2 pairings I could make for the test charge. And they're going to be either with the top or it's with the bottom. And by symmetry, we know they're going to be the same. So I'm going to call this like U total associated with the test charge. And again, a test charge doesn't have potential energy, but we're looking at the energy between the test charge and the 2 others. We just don't care about that internal big Q interaction. So it's going to be 2 times kqq over r. But r is not a variable here. The only thing we were given is that it's a distance x along the axis. So we're given that this distance was x, this distance was a. So we can find the distance r by hitting it with the Pythagorean theorem, or just Pythagit, as the kids say. That's slang for do the Pythagorean theorem. So 2 times kqq divided by square root x squared plus a squared. So that is our potential energy between each of the q's and the little q test charge. All right. Suppose now we just put it at a location x0 and let it go. So we know due to the force pushing to the right, it's just going to fly away. And we're going to be interested in that. So if I'm close to that midpoint, it's going to be a positive potential energy relationship. And I'm starting at rest. And then if I release it, and we're given that the test charge releases a distance very, very far away, if we ever say very far away, that's our indicator that U is equal to 0. And by energy conservation, this must mean that the energy is now entirely in kinetic. So we actually know our expression for U. Our expression for U was 2 times KQQ over x squared plus a squared. And our final kinetic energy, we don't know what the velocity is, so we'll call that 1/2 mvf squared. Derive an expression for the speed of the test charge after reaching a distance very far away. So once again, we got bar charts, so let's use bar chart energy conservation. So the sum of the energies must be a constant, because all of our forces are internal. So our initial energy with the test charge itself, because that's the energy that was actually changing, was 2 KQQ over the Pythagorean distance. And then K was 1/2, nope, K was not that, K was 0 at the start. Then U was 0 at the end, and kinetic energy 1/2 mvf squared. All right, now we can solve. So 1/2 mvf squared is equal to 2KQQ over x squared plus a squared under a square root. So we can not cancel the 2 because the 2 and the 1/2 don't cancel. So we would get multiplied by 2 divided by m and then take a square root, and we would get VF equals 4 KQQ divided by m times the square root of x squared plus a squared. So we get this interesting nested root relationship. Oh, and it does say that it was placed at a distance x0, so maybe I should go back and give myself a little subscript everywhere that there was an x0 in this problem. All right, there we go. So that is our very large expression for VF. So this is sort of the opposite of escape velocity. So now let's talk about that rather arbitrary choice I made, where I said let's not consider this potential energy associated with the 2 Qs. I did that because just like we only look at potential energies that change, doing that will just end up with the same sort of term added to both sides. So if you actually wanted to do it with the whole system, you wouldn't get a different answer, because instead you'd get an energy conservation that instead might look something like this, that says like, where your U0 is going to be 2 KQQ over square root x squared plus a squared plus the KQ squared over 2a from the charges by themselves, and UF would be 0 plus the 2 Qs are still a distance 2a away from each other. So we see that delta U works out the same because that term ends up canceling. So it's the same idea. Again, with potential energy, pick things that change. All right, so that is that.